Okay, so
Recording.
thank you. So our next speaker is Laurent Lacaze from Toulouse, who's going to talk to us about modeling immersed granular flows from discrete grain scale to continuous models. Laurent, thank you so much for accepting our invitation to give this talk here today. You can start your presentation. Thank you.
All right, thank you very much for the introduction. So first of all, thanks for the invitation to give this talk. So what I'm going to present right now is recent results that we have been doing on numerical simulation. So many things has already been mentioned in the previous talk. I think that maybe I will save time on explaining a few stuff about granular rheology and things like that. And this work has been done in collaboration with a few colleagues at in Toulouse, Thomas Bonomiti and François Chary, and several students. So I'm from IMFT. So IMFT is a fluid mechanics department in Toulouse, so southwest of France. And in the group I'm working in, many people are interested in geophysical flows, and especially geophysical flows involving particles. So for different kind of situation like debris flows, avalanches, submarine avalanches, turbidity currents, also sediment transport and ripples and dune formation. So all this kind of topic where they basically involved a particle. So when we start working on that, the idea was, can we first get an idea of what are the, let's say, similarities between all this stuff, and can we model using some viscosity model at some equivalent phase approach? Can we model this kind of geophysical scale flow, and can we extract actually what we need for this large scale model, which are basically closure models? So of course, this is roughly impossible to make some kind of a universal generalization of rheology or turbulence or any stuff like that for geophysical application. But at least we could start with really simple approximation, where we will consider that particular spheres. Basically, we have gravity, solid interaction, and fluid and Newton fluid interaction, and that's it. And we're going to work on really small canonical configuration where we just take into account some really simple process that we can encounter in this geophysical application, like a sediment bed of particle which is sheared by a fluid flow, or gravity-driven avalanches model also by column collapse, as presented in the previous talk. So obviously we are really far from geophysical application or anything like that, but at least we would like to understand some process at the small scale, so at the scale of the grain, and try to understand how we could predict basically what is important in this kind of shear flow, like in rivers, like when you have a flow in river and the intensity of the flow, how many particles you're going to transport, and how you're going to link the solid discharge of your bed load with the shear intensity. And in granular avalanches, basically one of the questions is to predict the length, the spreading length of evolution of these avalanches. So how can you predict some kind of spreading length as a function of the initial state? So they are basically the kind of idea of this tiny and canonical kind of configuration to try to extract this kind of quantities. And actually, I'm not going to talk about that really. What I'm trying to talk about today is basically, in both cases, what we know is that at some point, all these mechanisms leading to this discharge or to this spreading length are basically involving some balance between inertia of the particle and the dissipation of the system. And so the question is, what do we put in the dissipation? Just so basically, this is what was mentioned previously as a mu of I rheology kind of. So I'm just trying to see and to understand here how the model that has been found in the literature for this kind of dissipation process, like granular rheology or things like that, can still hold for the two configurations that I've been mentioning so far. And I will explain why we could have doubts on the reliability of this rheology on this kind of system, and where we have to be careful with, I think. So for that, one of the issues that we need to start from the description of the grain. So we need to start from the really small scale, so like using the DM as mentioned previously, so basically trying to model the trajectory and the dynamic of each individual particle subjected to some kind of gravity fluid force interaction with the surrounding fluid and contact with the other particle, and how from this dynamics we can extract accurate equivalent stress for a volume which is larger than the size of the particle. So this is the topic of this talk, and what I'm going to start with is basically to present really quickly the techniques and what we can find from the literature, and how I understand what we can find in the literature. So there's nothing new basically in here, and then I'm going to apply that for the two configurations I've shown. Like one is basically to mimic sediment transport, and the other one is to mimic avalanches. So let's start with the first one. So I'm going to go quite quick on this one because it's the same as what was present before. Is the DM method. So basically, what is expensive here is basically we expect to follow quite a lot of particles, and they are in contact with multiple particles. So this is the expensive part is often quite here. Then we have to model this contact force, so we have to solve that. So we need a really small time step to get access to this contact force, which is usually used like this kind of soft system. So there's other methods, but the simplest one for me is this one, which is we just allow some overlap between particles, that then we calculate the repulsive force between particles thanks to some linear spring dashpot system. And we have this important part here, which is in the tangential direction of the contact, where we have a Coulomb threshold basically, which is a friction law at the scale of the grain. So there's nothing very new in here. And the second stuff is, as mentioned previously, is how to model the fluid force. So how to extract some fluid interaction with some force interaction with the surrounding fluid. So there's a different approach. And the one I'm going to use here is basically based on, so it's not LBM, it's IBM. So it's immersed boundary method. So it's not like a Lagrangian method, but a Eulerian method here, where we solve the fluid phase at a scale which is smaller than the particle still. And then we can extract explicitly the fluid and the fluid force at the scale of the grain. So, okay, so this is a simulation. I'm not going any more into detail. So we assume that basically this kind of simulation works to mimic this kind of flow. So this can be discussed actually. I think I'm going to say that this is DNS, which is wrong. But for now, we will admit that this is roughly DNS method. So what we need then is basically from that, what we can extract something on a volume scale which is larger than the particle size. So this is what they call the spatial averaging method, and I think we have, I mean, the nicest explanation of all these different average method can be found in this book, which is really clear, I think, on the methodology. If you look in the literature, you can find quite a lot of different approach. I think the clear part is really in this book, in my opinion. So from that, you can extract at this volume scale, which is larger than the particle, some kind of equivalent phase for the liquids, the grains and the mixture. Which is important here is that the liquid is also an equivalent phase. This is not the liquid which is solved here. This is an equivalent liquid at a scale which is larger than the particle. And so from that, in this volume, in this small volume, then we have two phases. The two phases are basically quantified by their own volume, where we have involving a fluid fraction and the solid fraction in these two parts, where the solid fraction I'm going to refer to later is denoted phi. So okay, so from this simulation we solve everything, then we extract some averaging method to extract the stress and quantities at a scale larger than the grain. And what we need now is a way of trying to analyze the results that we obtain. And if we start, the idea is what has been done so far in granular material is to assume that the granular phase is somehow a non-Newtonian fluid, where we have an effective viscosity, basically, which is of Coulomb type, and that can be written then as a friction term times the pressure divided by the shear rate, as mentioned previously. And so everything is hidden here. The granular, the equivalent phase is hidden here, where we need to find out what is the effective friction of this material. And it has been shown in several studies that basically it depends only on one dimensionless number. This dimensionless number is called, for now 20 years, I think, the inertial number I. Everyone call it like that right now. Before it was called, I think, Coulomb number. I mean, changed name at some point. I don't know why, but it changed name. And anyway, in any case, it means that we just have one dimensionless number to consider in this system. And the idea of this inertial number is sketched here. If you increase the value, basically you're going to act differently during a shear rate. So basically, if you shear a particle which is on top of a layer of particle, small I means that you're going to follow all the small hole and roughness made by a row of particle. And if you increase I, basically the particle is not going to see anymore the hole in between the particle underneath. And so what it means, it's really simple from the sketch to see that basically when you increase I, basically the volume fraction is going to decrease because of that. And something which is slightly more complex, but can be also shown quite easily, is that based on this idea, you can show that you expect your friction to increase as long as you are smaller than 1, and then to decrease, basically. And this is what was observed and obtained in many studies. So basically, based on kinetic theory, we find that usually that the friction decreases as a function of I. And for small I value, we got this well-known empirical fit given by the group of Marseille, basically where we got this increase of the friction as a function of I. So nothing really new here again. I just recall here that this law is empirical, which is one of the issue, I guess, with this kind of system. It's really hard to find a theoretical model for that part here, while kinetics really provides some theoretical background, basically. Anyway, this is where I'm going to focus on right now, and to see how this part applies to the two configuration I've mentioned before. So the next part is how to account for the fluid phase. So the fluid phase, basically, if you look at in the literature, basically starting from ages ago. So we started with the mixture rheology of Einstein, and then Bachelor, basically we derived some effective viscosity of a suspension of particle into a fluid, where basically the suspension is really dilute, and then when we have a correction of the mixture to the order of phi, and then when you increase the fraction, then you cannot derive anymore any theoretical model on that, and you end up with some empirical model, such as this one, but there's a lot in the literature. But let's talk about this one, where you have this kind of evolution of the viscosity with the volume fraction, and where you have some divergence of this viscosity when you reach some critical volume fraction. So this is what I call here the mixture of viscosity, where I do not know what comes from fluid and what comes from particle. Okay. In these two cases, we can admit that basically they are the same. The mixture and the fluid are the same because there's no contact between particles. What I'm going to refer to the particle or granular viscosity is only the one emanating from the solid contact between particles. So these two one are they are really dilute with no contact between particles. They are the same. In this one, we don't know how to split these two contributions. More recently, people started to try to split these two contributions and to find out that basically we should have a mixture of viscosity, which is a sum of some fluid viscosity and granular viscosity. The question is what to put in this different system, and this is what we're going to discuss right now. So in the sediment transport, which is the easiest one because this is steady configuration. So we got this steady configuration of shear flow over bed. So we expect to transport a layer of grain, and then we have this system which is controlled by this different dimensionless parameter. Basically, the shield is usually assumed to be the dominant one because this is where we can find that discharge, solid discharge is usually related to this parameter. But the Reynolds can be important because when you change the regime of the flow, you can change this kind of flow also in between laminar and turbulent. And density ratio, I'm not going to discuss too much about this one. So this is what it looks like. I'm just showing a very quick video where there's nothing very fascinating. There's particle moving just due to this shear flow. All right. The only thing I wanted to mention here is the fact that I'm focusing here on a system in which the shear granular part is really localized to the top of the bed. So on let's say 4 or 5 particle diameter, which is really small. And this is where basically spatial averaging could fail. And this is what we're going to look at right now. So in this system, if you look at the stress over the vertical, so in this kind of imposed shear system, basically the stress has to be constant. The total stress has to be constant over the depth. And so basically what you obtain when you split your mixture contribution into the fluid one and the granular one is that you have at the top, obviously, only fluid. So you have a shear fluid that basically exchange with a granular one in a layer where basically particles are moving, and then you end up in the granular, in the bed where you don't have any more fluid stress and you just have granular stress, right, in the static bed. So this is how we split basically the two contribution, looking first at this one and this one. So I'm going to start with a granular one because there's nothing new to say about that. If we plot basically the friction law as a function of the inertial number that I called K here for some reason I'm going to mention here, it's not important. We obtain here in green is basically the empirical field that I mentioned previously that have been used for ages now in the literature. So this mu of I kind of flow, and we see that for all the Reynolds numbers, these numbers that have been covered into the simulation, basically we find that there's some variation, dispersion around this law, but they are quite small. So we can expect basically the friction law of the granular material to be independent of the flow regime. If this is true, then we are in a steady state. So we are at equilibrium here. So we have a single law of the friction as a function of the inertial number, and also a single, which is not shown here, law of the fraction as a function of the inertial number, meaning that actually the local rheology is only state dependent. So it only depends on the fraction phi. And this is what I show here. So again, we have a dispersion around a single law, but it seems to be reasonable to assume that we are at equilibrium and that the laws that are usually used in the literature still hold in this system, even if we are stuck to a very thin layer of moving particle. What is slightly different from the literature is that if we look at the fluid contribution in the system, if we look only at the viscosity of the fluid phase, then we can see that we still have an evolution of the fluid viscosity as a function of the fraction phi, as expected. But in this case, we have a strong influence of the flow regime. So basically on the Shields number and Reynolds number. And we can fit this kind of flow with this typical empirical model, which depend on phi, and where beta then has to depend on Reynolds and theta. So this is basically, we find that beta is a function of beta 0 plus some function of the inertia into the system. What is okay? Why not? But what is a bit surprising is that when we do that, we find out that the beta naught here is 0.6, meaning that if there's no inertia, if we go to viscous regime with no inertia in the system, we end up with this one is 0, and we end up with only this coefficient here, meaning that we don't find out the dilute regime, which should be expected to be 2.5 here if we want to recover, for instance, Einstein viscosity at small volume fraction. The reason for that is probably sketched here, is that we have to be careful in the system where we have really localized shear really non-homogeneous suspension, that using the result from homogeneous suspension is maybe a bit risky. And here what we see is that in my system, when I have a shear flow, basically the fact that phi is increasing is just due to the presence of particles at the bed of the volume. And there's not homogeneous. Basically, I just have particles which are only concentrated here, and the fluid shear is expected to be something like that. And the effective shear is shown here. And then if we compare both of them, then we find out that the ratio of the effective viscosity with the real viscosity of the fluid is some ratio where beta naught should be smaller than 1, actually. So this is what we obtain here, and this means that in this case, what should be put at the fluid viscosity is more likely to be something related to rough boundary layer than Einstein viscosity for an homogeneous suspension. And so what we obtain at the end is that if we combine everything, so let's say to go to the mixture viscosity, if we compare the mixture of viscosity obtained from the simulation to some model, so in this case, the Krieger-Dubertus, this is what we obtain. If we had a perfect model, it would mean that we would have all the dots aligned onto this line here, and we see that we have a dispersion, meaning that this model is maybe not that accurate for this situation. And if we try now to split the contribution and use the models that I mentioned before, it seems that it's slightly better, even if some progress is still required. And then we have to think of what's going on in this part. But it seems that basically we have at least make some progress on the description of the parts at small viscosity, basically. So this is what we have for sediment transport. And now I'm going so basically what we can learn from the sediment transport and really localized shear like that is, yes, we can use a classical model from the literature by splitting basically the fluid contribution and the granular contribution, but we have to be careful with the models that we put in these two contributions. In the Unsteady case, I'm going to talk about, and it's slightly different. So in this case, basically, we don't have localized shear. Basically, we have a bulk flow. Basically, everything is, we have a mass flow which is imposed by gravity, meaning that we don't have the flow which is really localized at the surface, but it's more like in the bulk. And in this case, we have a length scale of shear which is larger than the previous one. So this is a previous results I start with on the rheology, so which has already been mentioned in the previous talk, is if we look at the collapse, unsteady collapse, so what we have is an initial column here, collapsing and spreading because of gravity and reaching some steady state here. So we start with an initial time here and we end up with a final time here, and we have the evolution of time like that. So when we plot the rheology here, this is time dependent. So basically every dots here are taken at different position and time. And we have basically roughly the time evolving like that. So we start with an initial time where basically the inertia is zero, and then we have time increasing to some maximum acceleration of the system, and then we have a decreasing because of deceleration of the system, and then we go back to rest. So we have the time evolving in one way and then back. And we don't have any hysteresis in the dry case, meaning that the local and equilibrium state rheology works at any time of this collapse. Okay. So all right. So what I've presented before still hold for this unsteady configuration. Now, if we go to this experiment mentioned in the previous talk of the group of Marseille, and this difference between loose and dense initial packing. So I'm not going to talk about the dynamics and the spreading length and things like that. I'm just going to try to extract the rheology in the two different situations. This is what we obtained. So here I'm still plotting the friction as a function of the inertial number, which is now called J. So all right. And we have, depending on the situation, if this is an initial loose packing or an initial dense packing, we have very different trend in this case. We could imagine that in the loose packing, at least we are not that far from the equilibrium steady empirical model that I mentioned previously, but in the dense one, it seems to be quite different. So we have to be careful now. This is what I mentioned that before I said that during the acceleration phase or deceleration phase, basically we have exactly the same rheology, and we don't have any hysteresis in the rheology or in the states between the two phases. If we look closer at this viscous situation where the surrounding fluid becomes really important, what we get is slightly different. Is then if we split the acceleration phase, so the initial spreading of the granular mass, and we plot on another plot the phase where basically the mass is decelerating until it reaches its final state, then we have two different curves. So here we have on red, we have the initial one, so starting from the initial state, and we have time evolving like that. And in the other one, we have time back in this direction until we reach the final state where J is equal to 0. And we got all these different plots for the different situation. So what seems to be clear is that during the deceleration phase, it seems that we recover the equilibrium state, meaning that at some point, we have reached the equilibrium state of rheology with a given evolution of phi and mu as a function of J, which should be universal for granular flows. And it looks like basically in between loose and dense, we roughly have the same results. In the initial states, it's really different. The idea is initially we don't start with equilibrium because we start with an imposed fraction, which is phi I, which is not necessary at the equilibrium states, and then we need to relax to the equilibrium state, and this is what happened on a given time scale here. And in this case, in the loose situation, basically we end up with a friction which is lower than the equilibrium one, and in the dense one is the opposite. We end up with something which is larger. And the idea behind that is what has been referred to the dilatancy effect, where we should account in this system for some dilatancy, which is a difference in between the real local volume fraction compared to the equilibrium state one. This is what they call tangent psi here, and it has to be put to be added in the friction law. All right. The issue here is that what shall we do with that now? Because now we have something that depends on the local volume fraction, which is unknown basically in our system. So we cannot predict anything from that. The only thing we can say is that if we assume that this tangent psi can be written like that, and that the relaxation time on which phi is going to evolve is actually a viscous time scale, then we know that tangent psi is going to evolve as the inverse of j. Okay, but it doesn't help that much. It's just a scaling parameter. Then if we want basically to model the friction, we need to a time integration of this part, and this is what we don't want to do here. If we want to do that, well, then we could start putting that in a layer kind of simulation with a two-phase numerical modeling or this kind of system. If we want to predict without doing any numerical simulation, the idea here is basically to avoid this time resolution and to propose some kind of really empirical model based on the previous observation. So the only thing I'm doing here is I just say that I know that this extra term has to be inverse of j, and that it depends basically on the distance between the initial state and the equilibrium state. So basically what I put here is only a relaxation between the initial state and the equilibrium state, which is based on the time scale, which is basically in dimensionless term, exactly j. And if we plot that kind of stuff, then we can see that here you have in a solid line the prediction of the previous model, that we can capture the different states depending on the value of phi I, so basically the value which is here or here, depending on its distance with the equilibrium one. And this is what we obtained. So basically we have here this kind of curve when we are in dance, and we have a contribution of the friction which is larger, and the opposite when this is loose. And this is what I have so far on the rheology of dense granular material. This is what I wanted to talk about today. So basically, in few words, what I've shown is basically starting from simulation with techniques that I didn't really present, but that we have been using so far. We can extract the rheology of the system, and we can compare with some steady or unsteady configuration. And what we have found is that we have to be careful with the rheology when we are really localized shear and when we are basically unsteady. And so what needs to be done now is basically all that is how to implement all these results in a CFD kind of codes. And actually I like the last one is, does it really help in any prediction of sediment discharge or spreading lengths? It's not actually that clear. Maybe a constant friction law is basically enough, but we don't know yet. So this is something to be done. Thank you very much. This was a bit long. I'm sorry about that.
That was perfect, Laurent. Thank you very much. Very nice talk. So I think we have a few minutes for questions. Do we have any questions?
Thank you. May I?
Yeah, go ahead, Albans. Yes.
Thank you very much, Professor Laurent. Can you speak a little bit about the prediction of spreading length? Do you have any kind of technique or maybe some tricky to make this prediction? Because I have a student working with it, and I'm very curious if you can make some
you mean to predict
clearing.
You mean you want to, sorry,
the prediction of the spreading length for the sediment transport, for example.
You mean the prediction of the spreading length here in a granular collapse as a function of initial state?
Oh, I'm thinking more about the prediction of the length of saturation length in the sediment transport.
Saturation length. So yeah. So no, in the saturation length in sediment transport, I haven't been talking about that at all. In the situation I'm talking about basically, I'm expecting this saturation length to be zero. I'm expecting basically the particle here to act instantaneously on the shear flow. So what we would need to get the saturation length or saturation time scale is basically to look at what's going on during transient flow, when we start the simulation and how it's going to evolve as a function of time. As long as I'm steady, the saturation length doesn't, or saturation time doesn't influence anymore. And just again, I'm in a very viscous situation where the saturation length is not expected to be really important, not like in turbulent, basically.
Okay, thank you.
You're welcome.
Before we go to another question, I just follow up on Alban's question. So how long do you have to wait until you have steady results on your simulations, Laurent, on this case? Because it's very viscous, it's a very short time.
That's a good question. That's a good question. Wait a minute. Can I find it really quickly? I'm not sure about that. Yeah. Sorry. Can you see that?
Yes.
I'm showing a revision of an article. I don't know if I should do that, but anyway, doesn't matter. All right, so this is here, basically. This is here.
200.
So this is 200 based on the shear. Basically, this is 200 roughly.
Okay, all right.
And just of that. So this is where you have all the transients, and this is where I'm looking at the steady state. So what we have checked here is basically to look at this kind of convergent aspect here. Meaning that we look at the final state and we look on which distance basically we are not influenced by the initial state.
The initial state anymore. Okay, all right. Very good, thank you, thank you. Chris, go ahead.
Thank you. So yeah, very nice talk. I was wondering about you talked about the initial state and how whether it's dilated or compacted obviously alters the avalanche that you get in the column collapses. Once the avalanche has happened and deposited, can you accurately predict what the density of that deposit will be? So that, let's suppose we then inclined the whole container subsequently, would the prediction of the density of the grains be correct in the deposit of the first avalanche, such that if there was a second avalanche, if you then inclined the container, would it then predict that correctly? Or is this mainly looking at the transition from a static state to a flowing state without looking closely at what the predictions of the deposited density would then be of the material which was flowing and then become static?
All right. I don't know if I get all the question, but I guess you're talking about what is basically the volume fraction, let's say, of the final state of this deposit.
Yes.
So this is where basically I didn't. Okay, this is one of the tricky part of the system. What I show here is only things which has been moving in my system.
Okay.
So basically, the part which has been moving is going to end with the equilibrium state. So basically, the phi of I, and you're going to end up with a universal, let's say 0.59 volume fraction, but only on this black part here.
Yes.
This one and this one remain the same.
Absolutely.
And I guess that if we want to predict the final state, it's basically we need to split to predict what is going to move, so we can predict it based on the initial state, and how is going to be the final state depending on this initial state, basically. So I guess this is that. And if you now incline this part, I guess that the black one is going to flow quite quickly, while this one is going to remain static. So that's a good point. I don't really know, but I guess that's okay. What I haven't mentioned in my talk, I guess, is basically what's going on with the static pile. And the reason for that is that because I'm doing the mu of I kind of rheology, and we know that we don't want to. I mean, we don't know how basically to link exactly what has been flowing and what is really static.
Gotcha.
And that's it. So I can really only predict what is basically flowing in this system.
I understand. Do you think if, in an experiment, do you think it is true that the deposits of both of these avalanches would be a volume fraction 0.59? Or do you think that the deposit is actually deposited somewhere that is not quite at that that phi equilibrium?
I have no idea.
Neither do I, but yeah, no, that's interesting.
I have no idea, and I don't know how to check that, but yeah, it could be an interesting experiment actually to verify that. I don't know.
Yeah. Okay. No, thank you very much.
I don't know.
Very good.
But I guess it's basically everything which is still unknown on the hysteresis in between, avalanches angle and static angle and all the stuff. So I don't know.
Thank you.
All right, Laurent, thank you very much for this very nice talk. It was a pleasure to have you here. Okay, I will now
stop sharing.
Okay.